Hello, everyone. Rise and shine, everybody. Good morning, ladies and gentlemen, respected colleagues. Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome to today's webinar initiated by the National Research and Innovation Agency, or BRIN, in collaboration with Yayasan Konservasi Alam Nusantara, YEKAN. Now, I'd like to also welcome all participants to the second day of the webinar series titled From Science to Policy, Tropical Peatlands as a Key Role in Mitigating Climate Change. With me, my name is Alia, as the moderator for today's discussion. Now, for participants who just attended today, this is a series of webinar that is held for 3 consecutive days. We started yesterday on the May 15th until tomorrow, May 17th, 2023, in commemorating celebration the International Day for Biological Diversity, May the 22nd. Now, we have local as well as abroad speakers that will convey their presentations and results of the latest research on tropical peat ecosystems, which are an effective strategy for mitigating climate change. Now, at the same time, taking excerpts from learning in other countries regarding the implementation of climate change mitigation policies, which focus on peat ecosystem. Now, starting today's agenda, let us say hello to our speakers. Now, we want to say good morning or maybe good evening, Dr. Israr Albar, Deputy Director, Directorate of Land and Forest Fire Management, the Ministry of Environment and Forestry. Hello, Dr. Israr, how are you?
Hello, Ibu Alia Rahma. Thank you.
Hi.
I'm fine here.
Yes, it's quite an unusual time for you. You are in Porto, if I'm not mistaken, in Portugal. What time is it over there?
It's 2:30 something here, AM.
Oh, in the morning. So,
Yes.
wow, thank you so much for making the time for this webinar. All right, so welcome to you, Dr. Israr, and also I'd like to say good morning or maybe good evening. It depends on where he is right now. Mr. Andres Schmitz, Assistant Research Professor from Oregon State University. Hi, Andres. So what time is it from where you are right now?
Hello. Oh, it's 6:40, so in the evening. So it's a decent time. It's late, but still decent.
Okay, so just before dinner. So thank you so much for making the time as well for this webinar. And looking forward to see your presentation later on. And also, hello, Alison Hoyt, Assistant Professor from Stanford University. Welcome to you, Alison.
Hello, thanks so much for having me.
Thank you. Thank you for being here. All right, so I'm sorry about the airplane that just passes around close by. So we have all speakers joined right now. I invite all of you speakers for a group photo session. So kindly open your camera and give us your best pose. All right, so you're all here. Perhaps we want to ask Andres to also open your camera, Andres. I see Dr. Israr and also Alison, and there he is. Okay, so let me give a countdown from 3, 2, 1, and another one, maybe a different pose. Okay, 3, 2, and 1. All right, so I guess that's enough for the photo session. Yesterday we heard and discussed the scientific study behind the calculation of greenhouse gases from tropical peatlands with 4 researchers. And today, the main topic to be raised is science and policy for peat fire suppression. Now, for those with questions, audience, feel free to write it down on the question and answer column. And the committee will select 3 questions in stages to be answered by the speakers during the Q&A session later. However, we welcome the speakers. If you would like to answer the questions given and the Q&A box, you may also welcome to do so. All right, and we also have souvenirs available for 5 selected inquirers, hoping that you are the lucky ones today. All right, before we start, to put us into context, I'd like to give you some background on today's topic. Under normal condition, peat ecosystems contain 90% water and 10% organic content. The high water content keeps the peat moist, thus doesn't dry out easily. Meanwhile, peat that dries up is transformed into an effective fuel to trigger forest fires. Now, in 2015, forest fire incident has placed in Indonesia as the center of attention of the world community with a fairly massive area. Haze, reduced health quality, public activities disruption, ranging from teaching and learning activities to the economy, coupled with the loss of biodiversity and increased greenhouse gas emissions, are some of the direct impacts identified by the forest fires. El Nino in 2019, which has occurred again in Indonesia, is like that El Nino that occurred in 2015, but the number of hotspots and forest fires was quite large. This El Nino condition makes rainfall in Indonesia region almost non-existent. It was recorded that more than 80,000 hectares of peatland had burned, and the total area of burnt land as of 31 August 2019 reached 238,000 hectares. Now, the Ministry of Environment and Forestry, or KLHK, recorded peat forests and land fires in West Kalimantan reached 13,367 hectares during 2021. Now, that data was collected in January until November in that year. So in comparison to the year before, the number has increased quite significant. So given the facts, today we'll observe the presentations regarding the dynamics of policies and actions to reduce fires and the problem of transboundary haze in Southeast Asia by Pak Israr Albar from the Ministry of Environment and Forestry, and then followed by Andres Schmidt from Oregon State University, who will discuss the intensity, frequency, and severity of peat fires for 2 decades in Kalimantan. All right, so let's just begin with the first presenter, Dr. Israr. Although it's 2:30 a.m. in the morning, I hope you are quite awake and to start this presentation. So let me give you the floor for the 15 minutes ahead for the presentation. Go ahead.
Thank you, Mbak Alia Rahma. Assalamualaikum warahmatullahi wabarakatuh. Good morning, all participants. Still at night here. I would like to thank Sabrine and Hingga to make this webinar possible. I send my best regards to Andres and Elisa, as well as all participants in this webinar. I will share brief information about policy dynamics and actions in reducing fires and transboundary haze problem in Southeast Asia. Next slide, please. Forest and land fire occurrences in ASEAN countries are mainly caused by humans. We monitor the active fire occurrences day by day. This slide is showing the active fire in 2018-2023 on March 1st as an example. We noted that for the first quarter year in northern part of ASEAN experienced the fire season, and based on historical data, next fire season will move to southern part of ASEAN. Next slide, please. We analyzed the active fire data for the last 10 years, and the result showing that at least 5 countries, Indonesia, Myanmar, Laos PDR, Cambodia, and Thailand, contributed big number on active fire. The result also gave us information that on the north part of ASEAN, the fire season occurred during January, April, while in southern part, like Indonesia, occur in July, October. Next slide, please. Next slide. Peatlands in Southeast Asia encompass an estimated almost 20 million hectares, or approximately 50% of the world's non-tropical peatlands. This peatlands area can be found through Indonesia. This is the big part of peatlands in Southeast Asia, and also in Malaysia, Brunei Darussalam, with smaller areas reported in Thailand, Vietnam, Philippines, Cambodia, Laos PDR, and Myanmar. Next slide, please. The Fire Climate Change Initiative, Fire CCI, this is a project funded by ESA, European Space Agency, informed us that the average burn area in period of 2001 to 2018 recorded the highest number in Cambodia, Thailand, and Myanmar. So we can see here that Indonesia is the number 4 from this data for the average of the burn area. Next slide, please. The ASEAN Agreement on Transboundary Haze Pollution is a legally binding environmental agreement signed in 2002 by the member states of the ASEAN to prevent, monitor, mitigate land and forest fire, and to control transboundary haze pollution through concerted national efforts, regional and internal cooperations. Next slide, please. The haze-free roadmap on ASEAN in 2016 to 2022. Now we are in processing for the next 2022 to until 2026. This haze-free roadmap aims for a sustainable community that promotes social development and environment protection. The haze-free roadmap serves as a strategic, action-oriented, and time-bound framework for the implementations of the collaborative actions to control transboundary haze pollution in the ASEAN region. The APMS was prepared due to the pressing need for wise use and sustainable management of peatland, as well as the emerging threat to peatland fire and its associated haze to the economy and health of the region, and its possibility of contributing to the global climate change. This APMS now is also in processing to go to the next chapter until 2026. Next slide, please. This is also another document from ASEAN. The standard operating procedure provides procedures and guidelines for the implementation of monitoring and assessment and joint emergency response of the AATHP. We call it like a sub-measure. This SOP is formulated based on the above relevant provisions of the agreement. This SOP was adopted by the ASEAN Haze Technical Task Force in 2016, so it's already 17 years to be used as a regional SOP. And another one is the guidelines of peatland fire management was developed with the objective of providing a set of strategies to mitigate fires in peatland ecosystem and the ambitions of eventually overcoming the. Next slide, please. The ASEAN has adopted the zero burning policy in 1999. This publication provides guidelines on zero burning techniques, among others, based on commercial scale experience of plantation companies in Malaysia and Indonesia. Apart from the zero burning techniques, the guidelines also highlight the benefit, prerequisites, as well as constraints in implementing zero burning practices. You may see the second guidelines in the right side. So the ASEAN countries express their difficulties in implementing a zero burning policy at the local level, especially for local communities. Based on this, it was agreed to have a public awareness programs and develop guidelines for control burning techniques. The guidelines of on control burning are more aimed at local or small farmers and smallholders. Next slide, please. Indonesia has a strong commitment in tackling land and forest fire. The basis for this strong willingness, including ratification of Paris Agreement by Law 16/2016, and submitted its enhanced NDC last July. Indonesia has issued the Ministry of Environment Decree number 168, 2022 concerning Indonesian forestry and other land use, known as POLU, NETSING 2030 for climate change. Based on the enhanced NDC, Indonesia has targeted to reduce its GHG emission up to 32% or 43% with international support by 2030 with baseline of 2010. Next slide, please. From the target reduction, POLU contributing around 55% and energy around 39%. If we look at the BUR documents, peat fire contributed almost 50% as source of emission. From the POLU perspective, reducing hotspot, fire occurrences, burn areas, and peat management are the keys to reducing emission from peatland fire. So we know now how the importance of the avoiding the peatland fire. Next slide, please. The fire management consists of three aspects: prevention, suppression, and post-fire, where prevention is the most important by the important one. We have regulation in place, early warning and early detection system, supported by integrated patrol and ground checking at field, while campaign and capacity building should also be improved and enhancing skill and knowledge in land clearing without burning practices for local people. Next slide, please. Indonesia is the only country in ASEAN which is estimating burn area in monthly basis, both in Manara and pit soil. This graph showing the burn area during the last 6 years, where in 2019 were recorded the worst years of fire. This graph also showing us that the fire season in Indonesia occurs in July to October. We compare with the northern part of ASEAN, where the fire seasons occur in April to June. Next slide, please. We started to monitor forest fire in '97 as a ground station, receive satellite data established in Bogor office, and disseminate to fire-prone provinces through fax and email at the time. And then in 2001, all hotspot information flowing via mailing list Sipongi. And then in 2006, we moved the receiver satellite to Jakarta and edit L and X-band to acquire NOAA and Terra Aqua satellite. The first website for public access was launched in 2009 and relaunched in 2014 with the official domain name. Next slide, please. Indonesia has been developing FDRS, this is the fire danger rating system, for the last 20 years. And at the 2 years ago, BMKG as agency who's run FDRS now, launched the integrated and interactive forest fire warning system known as Spartan, included a radar product for the precipitation and a satellite product for hotspot, rainfall, smoke dispersion, and visibility. The information is useful for us to make a decision for preparing and mobilizing resources to prepare and conduct ground operations. Next slide, please. This is the Fire Brigade Mangalagni, which was established in 2002 in 5 fire-prone provinces and in 21 local fire centers. Nowadays, it has 34 local fire centers in 11 fire-prone provinces in Sumatra, Kalimantan, and Sulawesi, with the total personnel almost 2,000. Next slide, please. This is the Canarin. SEA has one in the Southeast Asia has monitoring. The Canarin node is the air quality sensing node, which is developed under the Canarin project in collaboration with Interlab in the IT Thailand. And then Leipzig, the Sorbonne University in France, and the University of Bologna in Italy. Up to now, there are at least 56 nodes available in 4 countries, Thailand, Philippines, Laos, and Indonesia. Next slide, please. This slide showing the use of digital tool to monitor and tackle land and forest fire in West Sumatra, Indonesia. The daily hotspot monitoring detected several hotspots in southern part of West Sumatra. On March 28th, we conducted ground check the day after, followed by fire suppression on March 30 to April 2nd. Our regular burn area estimation using Landsat and Sentinel-2 imageries clearly found the burn area at those locations, which verified by hotspot, ground check, and suppression activity coordinate. Next slide, please. This graph showing the ENSO index since 2010 to April 2023 and predicted to the next October 2023. It's showing that the second semester, there will be a chance of El Nino with index close to +1. For the last 3 years, we experienced the triple dip La Nina. Early this year, northern part of ASEAN experienced the fire season, and based on the historical data, next fire season will move to southern part of ASEAN. For the way forward, I encourage more collaboration in tackling land and forest fire and the establishment of the ASEAN Coordinating Center for Transboundary Haze Pollution Control will be the hub and the center of excellence for monitoring, as well as strong cooperation among ASEAN member states. So our aim to avoid land and forest fire could be achieved. The ACCTHPC will be hosted in Jakarta, Indonesia. For the last 3 years, yes, we are decreasing the hotspot and also the burn area This momentum and achievement on reducing fire incidents must be maintained and even should be improved. We still need to increase the fire prevention efforts and no more haze pollution as our commitment to meet the ASEAN haze-free. And to deal with land and forest fire, the scientific base is the bridge to policy-making process. To me, if I get lost in the decision-making process related to forest fire, the science and scientists are the place where I return. So thank you for your attention. Stay safe and healthy. Back to you, moderator, Mbak Alia Rama.
Thank you so much, Dr. Isra, and also for you. Stay safe and healthy, and perhaps a little sleep later on. Okay, and now we really appreciate your presentation, the information provided as well. We learned a lot about the government's effort, as well as programs related to forest and land fires from a policy standpoint, as well as concrete steps in preventing and handling it. Now, of course, this topic is not only of concern to us in Indonesia, but also in other countries as well, especially in the ASEAN region. All right, now let's carry on. We'll now have Andres Schmidt from Oregon State University to share regarding the frequency, intensity, and severity of peat fires for the last 2 decades in Kalimantan. Andres, we have 15 minutes and go ahead with your presentation. Hello, Andres. We can't hear you. Maybe you're still muted.
Yes, that's it.
There you
okay, sorry about that.
Okay, no worries.
So yeah, I focused today on a study that wanted to comprehensively look on the last 2 decades and see if there are trends in fire frequency or burn severity in the peatland or peatland forests of Kalimantan. So it was a joint effort between Oregon State University, the Nature Conservancy in Jakarta, the Ministry of Environment and Forestry and IBP University, as well as Ilahi Sciences International. So thank you to all my co-authors here that are listed here. So this is our study region, and we were focusing on the period from 2001 through the end of 2021, so 21 years exactly. And we're focusing on this area here in Kalimantan and the peatlands that you can see here in green that are based on the peat map data. That is roughly an area of 45,000 square kilometers, so quite a significant portion of the tropical peatland. We used 4 different workflows that we looked into that give us information about the physical causes and effects of those peatland forest fires over the last 21 years. The first one is we took era 5 climate data and as well as the Southern Oscillation Index time series and looked at climate anomalies and El Nino conditions, what Dr. Isra Alba also introduced briefly earlier. And we basically looked at how do climate anomalies that we find over those 21 years, how do they correspond to peatland forest fire frequencies? So this is what we found. There's a consistent, strong correlation between the Southern Oscillation Index here in green on panel C, as well as with the thermal anomalies. So what we see in panel B is the anomaly of the maximum monthly temperature. And what we see on panel C is the anomaly regarding to precipitation. So negative values means there is less precipitation than in the 21-year average, and high values show it's above the 21-year average precipitation. And on the upper panel A, we see the fire frequency. And as we can see, there's usually the years with lower numbers of fires, such as 2008 or 2010 and 16 or 17, for instance, coincide with years that exhibit also total precipitation amounts that are above the average and air temperatures that are below the average, respectively. So there's a strong correlation throughout this 20-year period that we analyzed. In fact, there is, on a 99% confidence level, the annual number of peatland fires shows a strong correlation with the anomalies of precipitation of 0.29 and 0.88 with the air temperature and 0.7 roughly with the Southern Oscillation Index. So clearly, the number of fires is strongly driven by those overarching climate conditions. The next thing is part 2, where we wanted to look not only on the fire frequency, but also on the intensity of the fire. So how much damage did the fires do to the vegetation? So we used MODIS hotspot data in combination with finer resolution data, 30 and 20 meter resolution data from the Landsat missions, various Landsat missions, and Sentinel-2 data. And we basically calculated burn severity for as many fires as we could find good satellite imagery for over those 21 years. And then looked again, how did burn severity evolve over the years? And, since it is such a long period of time, 21 years, we used Landsat 7 data. And then due to the fact that Landsat 7 after 2003 has some issues because the scanline corrector failed. So we enhanced that with the Landsat 5 data just to, get as many good imagery as we could get, high resolution imagery. Then it was complemented by Landsat 8 starting in 2013 and Sentinel-2 in 2015. So the further we go down this timeline, the more data we have available, which, is the nature of the thing. So what we basically did is we took all those fires and whenever there was a hotspot data, we looked for satellite data that was high resolution satellite data that was taken at the same area at the same time. And so we could find some pre-fire imagery as well as the corresponding post-fire imagery that we can find here. And using both, the red spots mark the hotspot data here, but that is a coarse resolution, roughly 500 meter data set. And the coordinates are not always very exact. So that's why we took a 2 by 2 kilometer frame around those hotspots and we're looking for each of those fires. We're looking for a high resolution Landsat and Sentinel-2 imagery. And then we calculated the normalized burn ratio and the differential normalized burn ratio using the pre-fire imagery and the post-fire imagery. And we did that for a little bit over 13,000 fire scenes. The importance was that the data quality for that needs to be relatively high. So only very little cloud cover is allowed. And of course, we need so we need imagery from not too long before the fire and not too far after the fire. So we can actually compare and see what the damage of that fire was, given that the vegetation starts to regrow quickly sometimes. So we had like a 60-day filter where we said, okay, for each fire that we find here from the MODIS hotspot data, we are looking for Landsat data within 60 days before and after the fire. Again, we did that for roughly 13,000 fire events. And that is what we found here. That is the frequency distribution now for the calculated DNBR, all pixels, the 30 by 30 meter pixel for all of those over 13,000 fires. And we used a burn severity classification that was based on, where's the, Hoskilo, there it is, Hoskilo et al., who did research in that area, and they really looked at ground data and looked after fires and determined in the field basically the severity of the fire. And that's the classification we used. We enhanced it though a little bit, and we divided the high severity class into moderate, high, and very high severity classes to get a final resolution for the high severity fires. So again, this is a DNBR range that we used, and the results show that during the last 7 years there is a strong increase in high and very high severity fires. Since we had 21 years, we used 7 years, so starting 2001 through 2007 and 2008 to 14 and 15 to the end of 21, and looked at all the fires that we had data for and calculated all the burn severities, and that's what came out basically. That is a relative distribution that clearly shows that we had a roughly 13% increase in high severity fires and about a 5% increase in very high severity fires in 2015 through 21, compared to the previous 7-year periods. So that was a little bit, of a surprise. It has to be said, though, that of course the 2015, as we know, was a very strong fire season that is included in the last section. So what we also did, that is not shown here, but we also used different time stamp, not just 7 years and another 7 years, but we did it with 3, 5, and other sections of the 21-year period, and it always ends up with the latest period having the most severe fires, or has an increased fire severity percentage-wise over all those fires in those 7 years. So after all, since it didn't make much difference, we used 7 equal lengths and divided our whole study period in those 3 elements. And yeah, the period again, the last period with the highest fire severities. As a third section, we used a fire model, and we used the most important, or for our study, most important land cover types. That is forest, the forests that were there from the beginning, and the converted land here as plantations, oil palm plantations, and successional grassland that the original peat forests were converted into. And we ran different scenarios, climate scenarios, with moderate fuel moisture and low wind, and then with low fuel moisture and low wind, and with higher wind and moderate fuel moisture, and then the worst case with low fuel moisture and high wind conditions, and model that for all those different land cover types and land use types. So, and we can see, sorry, I forgot to mention that we use the fuel and fire tool FFT model for that. And you can clearly see that if you look at the rate of spread, for instance, here, that the grasslands have the highest rate of spread. So when those natural forests are converted to grasslands, or oil palm here is an orange one, the rate of spread, so how far the fire spreads, increases significantly. The same applies to the flame length and to the reaction intensity, so the amount of heat that is produced per fire. So that shows that the converted land in most cases leads to a more fire-prone vegetation, depending, no matter what the conditions are, if it's low or high moisture, or low or high wind. Usually in all cases, the fire severity, so flame length, rate of spread, etc., is increased compared to the original peat forest. And a second step, or the fourth step, was now we wanted to look at the burned area in total. How did that evolve over those 21 years? So we took a MODIS data set, that is the MODIS burned area data set, but that has a limited resolution of roughly 500 meters, and that tells you, okay, is that 500 by 500 meter spot, is it burned or not? That's all it does. Israel Arbus Group helped us out. What they did is they delineated Landsat high-resolution data and Sentinel-2 high-resolution data and delineated it and calculated in that way manually, so to speak, the area carefully of each burned area. And then we could use that data that was collected over several years in about 49 districts in Kalimantan. And we basically calculated a regression between the coarse resolution data and that fine resolution area data, and found a strong, rather strong correlation and a good regression curve that we could use in equation. So now we took the coarse resolution area data and could correct it with that linear fit regression that was made based on very high resolution, or 30 by 30 meter resolution, where the area can much more distinctly and much more carefully be calculated. So we used basically that data to correct, if you will, the coarse resolution data that we used. And we can see that here in the corrected that despite the fact that some of the that the burn severity, for instance, increased, the total area burned decreased slightly for those 7 periods. Again, the latest period from 2015 to 2021 has lower total burnt area, peatland area, compared to the 2 previous 7-year periods. And you can see in gray the extreme years here of 2019 that was mentioned earlier, or 2014 here, with large burnt areas. But again, overall, the whole area shrunk a little bit. Reasons for that could be La Nina. There was a double or triple, actually, La Nina event here. So the opposite of the El Nino, where we had a lot of moisture and not many fires were burning so much. So that might certainly be a reason for that. Other reasons could be maybe the COVID year, 2020 here, when all activities, including agricultural activity, came pretty much to, well, not to a halt, but were much reduced. That is, that has been found in other published studies. So, you know, there could be several reasons why the total area decreased, and also the number of fires in some of those years in the later period. But again, the surprising part was that the burn severity of the fires was relatively increased, though, compared to the 2 previous 7-year periods. So in summary, the number of peatland fires, just the frequency of fires was found to be strongly correlated to the air temperature and reduced precipitation, as they happen with El Nino events, for instance. That is not surprising, but it's, you know, it's proof of concept basically of that long period that we looked at, where, again, as shown earlier, the number of fires was always related to the precipitation and the anomalies of air temperature. A comprehensive increase of the whole area, peatland area of Kalimantan, showed that the high severity fires increased by 13% on average in the most recent period from 2015 to the end of 2021 compared to earlier 2 periods. And the total peatland area burned, however, decreased for that period by roughly 20% on average compared to the 2 7-year periods, the prior 7-year periods. And the fire model clearly shows that an increase in fire intensity, in flame lengths and rates of spread was shown for grassland and oil palm plantations compared to the forest stands they replace. That, of course, leads to a decreased fire resilience of degraded peatland and increased proneness of fire of those converted areas that are converted again to oil palm plantations or grass and shrubland. While I haven't shown that here, we also looked a little bit at political frameworks. How do they affect the number of fires over the years? Due to the shortness of the presentation, I couldn't focus on that as well. But basically, the recommendations for a better peatland fire management are more focused on fire prevention activities, clearly, improving the availability and accessibility of funding for pre-fire mitigation, suppression, and fire recovery, obviously on regional and local scales. And an alignment and harmonization of government regulations at the national and regional levels. Thank you again for all the people who contributed to this long-term study. Thank you.
Andres, thank you so much. And it's also very interesting to learn about the modeling of the peat fire in Kalimantan, where the study was conducted for 21 years. And we happen to know as well that from your study, the last 7 years was showing quite a severity increase fires, and also the converted lands are more prone to fires compared to the original peatland. And again, if anyone would like to have questions addressed to any of the speakers, it is you can always use the Q&A feature below and just comments, put your questions there, and Baisrar or Andres or later on Alison could answer your questions as well. All right, now let's move on to the next presentation. New data sets to investigate drainage, subsidence, and fire risk across Southeast Asian peatlands. We then explored opportunities to leverage these data sets to evaluate the peatland rewetting potential. And without further ado, those will be included in the presentation from Alison. We welcome you, Alison Hoyt from Stanford University, to give your presentation for about 15 minutes. The floor is yours.
Thank you so much for the invitation. I'm going to go ahead and share my screen. Do you see my screen?
Yes, we do, Alison.
Perfect. So today I'll be talking about drainage, subsidence, and fire in Southeast Asian peatlands. And I'd like to acknowledge my many co-authors that were too many to fit here, as well as my Indonesian collaborators. In my research, we focus on understanding how peat carbon stocks and greenhouse gas emissions respond to climate and land use change. And we approach this problem from both the process understanding, so trying to see what drives these fluxes and how might they change as a result of climate and land use change, as well as by developing new data sets at local, regional, and global scales. And we hope that putting these together can help us improve management. So today I'm going to talk about 3 specific data sets, one on subsidence and CO2 emissions, a second on soil moisture and fire risk, and finally a new data set on drainage networks, which were each developed with teams of collaborators. And then I'll talk a little bit about how we can put these together to inform peat rewetting priorities, hopefully using this high resolution spatial and temporal data to make better decisions. And I'd like to mention that this part on peat rewetting priorities is still a work in progress. So I welcome your questions and feedback as we're developing this to see what directions would be most helpful to the community. So as you all know, peatlands are large carbon stocks, and this below ground carbon accumulates over thousands of years. But this old peat carbon is being threatened by land use change, and a lot of the deforestation is particularly concentrated in coastal areas where peatlands are also present. And this means that drainage tends to go hand in hand with deforestation in these peatlands, and that lowers the water table, introducing oxygen and therefore aerobic conditions that speeds up decomposition and leads to CO2 emissions and fire. So a big part of our work is to understand these mechanisms as well as to quantify the emissions that result. So based on work on subsidence that I'll talk to you more about, we quantified the greenhouse gas emissions from peatland drainage and found that it was similar to fossil fuel emissions from the same region. And there's also been a lot of work done by many of you and others on fire. Today, what I'm going to talk about is how we can use the data sets that we've developed to quantify this peatland drainage and degradation as to inform peatland rewetting, which offers an opportunity to slow down these CO2 emissions and fire. We have mechanistic understanding that shows that when we raise the water table, we expect CO2 emissions to slow down or stop. So here, for example, on the x-axis, you can see water table depth, and this is data on CO2 emissions that shows an increase in CO2 emissions as the peat dries out, while there's very negligible CO2 emissions under wet conditions. And that's what really motivates a lot of the work on peat rewetting in addition to fire suppression. What I also wanted to acknowledge is that we can still get a lot of gains from partial rewetting. So even if we're not able to raise the water table as much as we might like, there can still be a reduction in CO2 emissions as a result. So I'd like to also discuss this compromise with the audience and hear what people have to think about that. Peatland rewetting offers a low-tech and low-cost intervention, and that's part of the reason there's been so much enthusiasm around this approach. And it's also been highlighted as a cost-effective mitigation opportunity in much of the work reviewing natural climate solutions. But the challenge is that there's a huge uncertainty in how much peatland rewetting costs and how successful it may be. So here you can see from this review paper that the error bars on the opportunities for peat restoration are enormous. And this is especially compared to other natural climate solutions. And this is in part because tropical peatlands are so diverse. Here you can see landscapes that I'm sure many of you are familiar with, from smallholder agriculture to burned and degraded areas to oil palm plantations getting established. And across these different landscapes, both the emissions of greenhouse gases as well as the cost for rewetting are highly variable. And so one of the goals of our work is to identify priority areas for peat rewetting and to help build tools that could inform where can the largest emissions be avoided most cost effectively. And so to answer this question, we are interested in leveraging 3 new data sets that I'll discuss in more detail now. As I mentioned, on subsidence, soil moisture, and drainage. And I'd like to particularly acknowledge Alex Konings and Nathan, who led the work on soil moisture and drainage networks, along with a number of other collaborators, including Alex Cobb, who's another one of the panelists for this webinar series. So first, I'd like to discuss subsidence. This is a measurement that we can use to understand how fast peat carbon is being lost and how CO2 emissions from peat oxidation vary across the region. So it's well established that drained tropical peatlands are subsiding. This has been monitored for many decades, as for example, you can see here with this subsidence pole showing 2 meters of subsidence over time. And this presents both challenges in terms of compaction, CO2 emissions, but also flooding risks for low-lying coastal peatlands. In our work, we went beyond these pole-based measurements that exist in the region to develop the first large-scale observations of subsidence across diverse tropical peatlands. And we used an INSAR remote sensing approach, that's interferometric synthetic aperture radar. And this allowed us to make almost 2 million measurements across 2.7 million hectares. And by doing this, we could access a range of different land uses and remote areas that previously were more challenging to access with pole-based measurements. And also we could just increase the amount of data that we had to get at typical subsidence rates and spatial patterns. So here's examples of the time series that we found. So on the x-axis is time in years. So this is, for example, a 2.5-year time series. And on the y-axis is the total subsidence. And you can see, for example, in this example of a non-peatland area that we selected, that there's no subsidence, just as you would expect. While in contrast, the drained peatland was subsiding substantially, nearly 10 centimeters in these 2.5 years. We can use this type of time series we get at every single point in our study area to map subsidence over large areas. So here's an example from North Sumatra, and you can see the peat outlines are hashed with peat domes between the rivers in the black lines, and the colors represent the subsidence rates. So in green is low or no subsidence, and then high subsidence rates from 2 to 4 centimeters in yellow and red. And every one of these colored pixels represents the average subsidence rate, which we get from a time series, as you can see here and as we saw on the last slide. So this is really exciting because we suddenly have much finer spatial resolution to help us understand subsidence in these areas. This can be used for a lot of different things. One example is it can help us to identify hotspots of subsidence. It can also help us to look at patterns with different land uses. So for example, we commonly find that subsidence changes follow land use boundaries. So this is on the left, a subsidence map with our highest subsidence in the red and purple colors and lower subsidence in gray. And on the right is a land use map, and you can see that the high subsidence rates in this case follow the land use boundaries, where the purple is a plantation, while the adjacent area is a degraded forest. So we didn't see that certain land uses were always had higher subsidence, but instead we saw that there was a patchwork across the landscape, but land use boundaries were really stood out. We can also use this information to calculate CO2 fluxes from peat oxidation. Because the method only captures the long-term subsidence, so we cannot capture the initial subsidence that happens immediately following drainage and deforestation, which would be largely driven by compaction. So we're only capturing this long-term subsidence that's primarily driven by loss of peat carbon or peat oxidation. And so based on this, we can calculate the CO2 flux with factors from the literature for oxidation, bulk density, and carbon content. So before I talk about the next data sets, I wanted to summarize what we found in our subsidence data set. We found that we can identify hotspots and we can measure subsidence rates in remote areas. And using this information, we can also capture CO2 emissions resulting from peat oxidation from drainage. Next, I'd like to discuss another data set on soil moisture and fire risk. And this can help us to understand how fire risk varies in space and time. And as I mentioned, this work was led by Alex Konings and Nathan Tidak. As not unexpected, we know that drained dry peat has high fire risk. But figuring out where the drained peat, where the peat is driest and when it's driest is still a challenge. So we found that soil moisture can be mapped using microwave remote sensing, and we mapped soil moisture across Southeast Asian peatlands. This is an example of the types of maps that we were able to generate from this data. And in contrast to the subsidence data, it's a much coarser spatial resolution, but we can actually track the changes in soil moisture over time. Here's an example of the time series that we can derive from this information. So you can see that soil moisture varies over time. And if we put all of these different time series from different pixels together, we can also use them to see how they correlate with burned area. So here again on the x-axis is a time series, and on the y-axis is the soil moisture value. And you can see soil moisture goes up and down. And then in the color is the fraction burned area. So in this dry period, when soil moisture goes down, we see the highest rate of fires. So there's a strong relationship between soil moisture and burned area, with burned area varying inversely with soil moisture. And if we put this relationship together across the region, what we can see is this almost threshold behavior where below a certain soil moisture, we see much higher burned areas. We also checked to see if this relationship was predictive. So if we look at soil moisture, for example, a week in advance, 10 days in advance, 20 days in advance, can we still predict what the likely fraction of burned area is? And we found that it was predictive up to 30 days in advance. We also were excited to see that it mapped on very well with the relationship that we found, or that others found in the lab, where there was a threshold of soil moisture and peat burning in lab studies. So you can see that these two mapped onto each other very closely. So in summary, we mapped soil moisture over time across Southeast Asian peatlands, and we found that soil moisture can predict the fraction of burned area and fire up to 30 days in advance. Finally, the third data set I'd like to share is our work on mapping drainage networks. And this allows us to look at what is the extent of peatland drainage, and also to think about how we might be able to use this information, for example, to estimate how much rewetting would cost. So again, we need high spatial and temporal resolution to map drainage canals. So we used planet data, which is at 5-meter resolution. And this can help us, and it also has a daily revisit time, which can help us to overcome clouds and smoke to be able to see drainage canals in satellite images. So this is an example of what the data looks like. And you can see that we can label these canals and roads by hand, but that's very time consuming. And so we collaborated with computer vision experts and used a convolutional neural network approach for classification. And this is an approach that's also used for mapping roads. So you can see, for example, what the data looks like here. This allowed us to make the first systematic region-wide map of drainage canals. Previously, the maps were much more localized or patchy, but now it's been done in a systematic way. And you can see some examples of how variable the drainage networks are in different regions and different land uses. You can also zoom in, for example, here's the Malaysia-Brunei border to see how some areas are more intensively drained than others, depending on local policies. We aggregated this information to a 1-kilometer scale to map the drainage density across the area. And we found that the land use type, so for example, plantation or smallholder or degraded forest, was not a one-to-one predictor of the drainage intensity, which is not surprising, but it's exciting to see how variable this is and to actually be able to pinpoint individual locations, which can help us for more specific management or to ask more pointed research questions in the future. We were also able to correlate this information with the drainage canals, and we found that more intensive drainage is related to higher carbon emissions. So here, for example, on the x-axis, you can see the subsidence rate from our previous maps of subsidence. And on the y-axis, you can see the probability, and the highest, the most intensively drained, for example, in dark brown, has the highest subsidence rate, with decreasing subsidence rates as drainage intensity decreases. So in summary, we were able to develop the first regional consistent mapping of drainage networks. And we found that land use was not necessarily a good predictor of drainage. And we hope that these networks and maps can be used to calculate rewetting costs for other purposes in the future. So putting these all together will allow us to identify cost-effective peat rewetting opportunities. As I mentioned, we're really interested in understanding where can the largest emissions be avoided most cost-effectively. And at a most simplistic level, we can take the cost of restoration and divide it by the avoided emissions, both from peat oxidation and from fire, using these data sets. We're also interested in the social, economic, ecological, and health implications and costs. And then hopefully by putting all of this together, we can create maps where different stakeholders can consider where the peat rewetting might be cost effective and combine that with information on where it's most socially and politically feasible to target peat rewetting projects. This is an example of how we can put this information together. So we can combine canal blocking costs with information on peat oxidation emissions as well as fire emissions. And what's really exciting here is that we have these data sets at extremely fine spatial resolution compared to what has previously existed at a regional scale. We also need to consider other benefits, for example, the avoided health impacts from PM 2.5 during fires, avoided damage during fires, and employment for dam construction. And we're thinking a lot about the fire models that we want to use to infer future fire risk. As you know, there's also important social and health implications from fire. So we are currently including that, but we'd also be open to ideas on how to include it more thoroughly. Here's an example of the preliminary maps that we have. Some of the challenges that I'd love your feedback on are how to refine the costs of rewetting, how to consider the burn depths in the future, because we believe that as fire is more frequent in a peatland, it's likely that the subsequent burns are not as deep as the initial burn, but there's actually very limited field data and only from a few places on burn depth. And finally, we're thinking now about accessibility in terms of these results. How can we make them most useful to people?
Okay.
And another aspect, most of the work I talked about today was remote sensing work, but we're also partnering with Indonesian partners to do field validation because, of course, we need to know how well greenhouse gases are reduced and how well canal blocking is working in practice in the field.
Okay, Alison,
so to summarize,
yes, the time is very limited, unfortunately.
Thank you so much.
Thank you.
Yeah, we found that these data sets could be really useful to inform peat rewetting. So thank you so much.
All right, Alison, thank you so much. So on that note of your presentation, to have a well-managed peatland area, we need accurate data information about the area itself, and mapping constitutes an integral component of the process of managing land resources, and mapped information, which is the common product of analysis of remotely sensed data. And with the right technology, we could obtain data and information quicker than decades before. Once again, thank you so much, Alison, for the presentation. So, ladies and gentlemen, colleagues, we have listened to comprehensive explanations from our three speakers together. We now enter the question and answer session. And on my hand, I have three selected questions from the committee. And if there's time left, we will address more inquiries. All right, so I see the questions here. I have actually one question and another bonus question for Pak Israr. Okay, I'm just going to read out the questions to you, Pak Israr. Are you still here with us? I hope.
Yes, Mbak Rahma.
Okay, great.
Please, go ahead.
Okay, so the first question, is controlled burning still permitted on peat? How to monitor land clearing by hiding from this policy, even though they're burning, but not in a controlled manner? So that one is from Wahyu, from Brin. And should I just go ahead with the second question, yeah? Yes, second question will be, in tackling the occurrence of peat fires, which can increase air pollution and greenhouse gas emissions, what technology can be developed to be a solution to this problem? And what role should be played by the government in helping to overcome the problem of peat fires, which cause widespread air pollution? So that was a question from Sukur Abdurrahman from University of Sriwijaya. Okay, so those are the two questions for you, Pak Israr. Go ahead with the answers.
Okay, thank you, Mbak Alia Rahma. So for the first questions, actually, the burning the fire is not permitted, it's not allowed, both in mineral and pits. So we then also have the knowledge on control burning, or in the UK, we call it the prescribed burning. However, this burning or the fire is the habitat management if we talk in the science base. But Indonesia itself, like in the law number 41/99, it's about forestry, it's not allowed to do fire. And also there's like the government regulation number 45, 2004, concerning the forest protections. It's also saying that no fire in the forest. So everyone is not allowed to do fire. So that's why we don't have the we are not allowing the control burning even for the fire itself. And to tackling the occurrence of peat fire, what we can do is, to maintain the pit to maintain the water level in the peatlands, and then the important thing also is how to involve the local community to prevent the fire, because as I mentioned before, since 2016, the government of Indonesia now focusing in the prevention, not the suppressions, because the suppression is very, very high cost. And I think most countries cannot afford to prevent the fire by themselves if it occurs and widespread in, very fast. That's my answer to Pak Sukur. So I think we need to do the peatland management, especially in the peat fires occurrences. Thank you, Mbak Aliahma.
Thank you very much, Pak Israr. Still very sharp at 3 o'clock in the morning. Now let's move on to the next question, and this is addressed to Andres. Okay, so I'll just read out the question for you, Andres. If we have data on forest and peat cover by using spatial dynamic modeling based on the pattern of use of forest areas, and we have forecasting climate data for the next 100 years, is it possible to do this as an early warning system in preventing forest fires? That is from Herdianti Indah Puspita. Go ahead.
Well, that is a difficult question. Very good question. Thank you, though. Modeling or predicting fires, whether those are peatland fires or other fires, is always difficult. But for all models, whether it is a machine learning model or a process model that actually tries to, simulate the actual processes that happen as opposed to a statistical model, those always use climate data that you mentioned. So that would certainly be a very important input. With fires, well, first of all, yes, generally yes, but there are difficulties. For instance, fires or wildfires are caused often by humans, and then you don't know exactly when and where humans will ignite those fires. Or they can even be also be ignited by thunder and lightning. Then you also rarely you can predict where it is. What you can possibly do if you know the land cover for the future and the corresponding climate predictions for the future, which has to be said are also usually suffer from a huge uncertainty if you go far into the future. But generally, those two things will, of course, play a role in fire risk prediction. So you can try it, but looking 50 or even 100 years were mentioned ahead, that is extremely challenging due to the many unknowns that are beyond land cover and climate, which again are important but not solely. It seems very challenging, but of course you certainly would need the future land cover and, of course, the future climate. As we have seen in other data, there is always a very important impact, of course, on burn severity or on burn probability and fire occurrence. So yes, you can. How well it can be done is, depends on the data quality and all the many unknown aspects that might play a very big role if it comes to peatland fires, where of course the political framework or the permission or no permissions and, the enforcement capability of a nation on a regional or local scale, where even if it's prohibited doesn't mean it doesn't happen. So, many unknowns are in there, but so if you have those data, short and brief, as short as I can answer it, yes, it's important. You need them. 100 years in the future, probably not. That probably won't work that well.
All right. Okay. Thank you so much. That it's doable but quite challenging. Thank you, Andres, for the answer for that question. And now I also have questions for Alison. You have 2 questions here that I received from the committee. The first one is, while the the first one, based on the results of your research, what peat variables are really needed to develop a fire early warning system or to monitor the GHG emission? How about the variables of community characteristics and behavior? That is from Wahyu, from Brin.
Yeah, thank you so much. As we saw, there's a strong relationship between soil moisture and the likelihood of burning, but whether something actually burns or not, of course, is largely due to social considerations as well as some chance factors. And so I think with the soil moisture, we can highlight high risk areas, but then further monitoring on the ground of those high risk areas would be needed to catch actual fires.
Okay, and we still have the next question for you, Alison. While CO2 is reduced greatly from full rewetting, CH4 emissions likely increases as well. What are your thoughts on the compromise between the CO2 and CH4 emissions with regards to their GWP? That is from Jonathan from NUS. Go ahead.
Thanks. Yeah, that's a great question because methane is such a potent greenhouse gas. I think in this case, there's a lot of interactions between land use as well. So considerations on whether you want to raise the water table to the peat surface or above the peat surface may also depend on whether the land is being restored or is still under some agriculture or fertilization. And another consideration is that as long as the water table is just below the surface or deeper, then it's likely that the methane will be oxidized rather than reaching the atmosphere. So the methane is usually primarily escapes when the water level is at or above the surface. And so we see that even in most rewetted peatlands, the water table is only above the surface for a very small fraction of the year. So I think the balance is still in favor of rewetting as much as we can from a greenhouse gas perspective.
All right, Alison, thank you so much. Seems like we have some time that allows us to have more questions accommodated. So I have one here for Dr. Israr, once again. So Dr. Israr, here's the question for you. In order to improve the prevention efforts, the meso level and the local district to village level initiative and participation is definitely crucial. However, the current model of fire and peatland governances is very much central government or top-down approach. How do you see the opportunity to improve the local initiative and involvement, be it program budget, monitoring, etc.? That's from Al Fajri, University of Islam, Riau. Go ahead, Pak.
Okay, thank you, Mbak Rahma, and also Pak No Fajri in Riau. I think Riau, Pak Fajri experienced a couple of years of the fire season in Riau, or in Pekanbaru, of course. And, that's our policy. It's national policy, and we have the provincial and also the district policy. What I have found is the village policy could also be involved in this fire prevention. Like in Dayun, Siak, it's in Riau. I found that the head of village is good capacity in making changes in fire prevention. I mean, he could also gathering all stakeholders, not only the local community, but also like the bankers and also the company, the private sectors, and then hand in hand together to prevent the fires. So I think the Dayun in Siak is one good example, and how the head of the village could encourage the local community in prevent the forest fires. And we know in 2014, 2015, the Dayun in Siak is the fire-prone village. It's about 85,000 hectares. And then now it's very rare in the fire occurrences because of the policy of the head of the village that could also involve all the stakeholders in their area. So I think that's a good example that we can replicate to another village, not only in Riau, but also to other provinces. Thank you, Pak Alia Rahma.
Thank you, Dr. Israr, for the answer. And I can still sense that the enthusiasm is still here among our audience. So we have one more question, and this one is for Andres again. Andres, so here's the question for you. What do you think is the major drivers for peat fires in Indonesia? A lot of people said that the peat fires cannot occur without external intervention. For example, cigarette litters. Could peat fires in Indonesia occur naturally, i.e. from dry litter, friction, or lightning? From Ajeng, from the IPB, Institute Pertanian Bogor. Go ahead, Andres.
Well, first of all, I'm not an expert in fire, ignition in Indonesian peatlands. Well, certainly there is fire occurrences from lightning and such. So, so what was the question again? Sorry, I think I lost my train of thought.
Yeah. So her question was, can peat fires, or could peat fires in Indonesia occurs naturally, for example, from dry litter, friction, or lightning?
Yes, yeah, they can. I mean, not all fires, peat fires are only human ignited, but that is obviously the problem, where the largest damage was done and the largest fires occurred. But we know, and it has been shown, that climate itself, or it's larger regional climate phenomena such as El Nino and La Nina determine the fire conditions and also the fire risk. There's a reason why the most fires occurred during those dry seasons, not only because people decided to burn more fires in the dry season. So yeah, they can be ignited unintentionally as well, or not by humans who try to convert forest into something else.
All right, thank you so much for the answer. Hopefully it answers everything, especially not only from Andres, but also from Dr. Israr and also Alison. And 20 minutes have passed. Time really flies when you are having fun. Hopefully everyone is having fun. And thank you for your contribution to our discussion today. Hopefully with the information we received today, we can understand better the situation of peat fire and how the Indonesian government has strengthened the efforts of mitigating, preventing, and responding to disaster. Okay, and now as a conclusion today, the problem of forest and peatland fires is not only an environment problem, but is also closely related to human life and climate change. Now, the Indonesian government takes this issue seriously from a policy standpoint and directly handling affected areas and across countries. And our priority to prevent peat fires is to keep the peat wetted. And the most important thing is to involve all stakeholders, including local community, since the land and forest fire in Indonesia triggered by human activities the most. Now, strengthening of infrastructure, community capacity, and cooperation between institutions play a big role in providing permanent and sustainable solutions. Appropriate policies and the use of technology and science are needed to prevent and deal with fires in peat ecosystem. Now, those are some key takeaways that we get from today's presentation. And respected ladies and gentlemen, would like to express our gratitude to all of the speakers today, especially those who are speaking on the time that is not very convenient to wake up. So we do really appreciate that. Also for Andres and Alison, thank you, Dr. Israr again. And I invite all participants for tomorrow's event at the same time arrangement, starting 8:30 until 10 Indonesian Western Time. And there are going to be 3 experts that will be sharing their research from Professor Dr. Gusti Anshari from Tanjung Pura University, Pontianak, West Kalimantan. We will also have Alex Cobb, Center for Environment Sensing and Modeling, Singapore MIT Alliance for Research and Technology. And we will also have Bondan Winarno, researcher from Ecology and Ethnobiology Research Center from the National Research and Innovation Agency, or BRIN. Now, again, thank you so much. Hosted by myself, Rahma Alia, with thank you and see you tomorrow. Salam Lestari. Bye.
Bye. Thank you.
Bye.
Thank you.
Thank you. Goodbye.
If you don't manage development, you lose nature.